Okay, so we start the class. So first, the midterm. I graded midterm last week. And question 1 and question 2, the overall, that you did well. And the grading is a little bit strict, especially for the explanation on statistical analysis. And question 3, maybe a smaller number of students got better scores. Maybe one reason is that you run out of time to the question 3. And another reason is that the question 3 is more like the real data analysis. So the data handling is messier and it takes more time, and you have to be careful about everything to get the meaningful results. So I think that that's the difference between the classroom statistics and the real data analysis. So I think in any US schools that you can study, practical knowledges, but still there is a gap between the knowledge and the hands-on experience. And the problem 3 is more like hands-on experience. And for the last question, in question 3, I asked you to develop a better model to predict the default risk. And actually, the only 2, entirely valid the results. The one by the Brennan and the other by Tsai. And so you two did very well. About coding, and also that you developed a good model with the interactions and the variable selections. And some others are really close to the right answer. I think the Mariam and also the Connor, and I think another student, Connor, Mariam, and the Rajesh, I think. So those 3 are really close to the perfect, the entirely correct answer. I think the Mariam and Rajesh is the result good for data competition, where the evaluation will be done by the administrator. So the model itself is valid for those people. Yeah, and that is the midterm. And I don't release the solutions, but you can ask me where you lost points or where you got points. So I graded on paper, so it takes so much time. So usually for midterm, I printed all of your code and the grade on paper. So I have the graded, I think the midterm at hand, so you can ask me details of my grading. Yeah, and final presentation. Maybe I have to share the screen. Actually, one student has some time conflict on April 19th. So hopefully, if any of you can switch to April 19th, that's the best, but I don't know if it's possible or not. I don't know. Shiv, did you send me an email? Maybe. I'm not sure. So anyone who are supposed to make a presentation on April 28th can present the result on April 19th? No. Any? No.
I don't think I sent you an email, but I'm not sure if I'm able to make that.
I see. So you have some time concerns, or just you're not confident to make presentation on the first day or something like that?
I think I have, it's not time constraints. I think I'm busier during this next month. So I see. I think it's just a confidence thing. I'm not sure if I'm going to be done by the 19th.
Okay, yeah. Generally, some students sometimes they drop the course, but the presentation is earlier. Actually, the risk is lower, at least in the past. So I don't know. If you have many final exams, then probably earlier date is better. But if you are not comfortable, I understand that. But yeah. Okay. Or how about anyone who are scheduled on April 21st? Any of you can switch to 19th? No.
I can move to the 19th.
Oh, okay. Sorry. Who said that?
This is Rajesh. Rajesh,
Sorry?
the 28th.
Rajesh? Sorry.
Yes.
Okay. Thank you so much. So Rajesh to 19th. Okay. So I will write down. Okay, so that's the final presentation, and yeah, probably you have difficulty. You had difficulty to you may have difficulty to make a final project plan because we haven't covered all chapters of the textbook. So just I explained briefly about what will be covered in chapter 8 to 10. And chapter 8 is tree-based methods, and chapter 9 is support vector machines, and chapter 10 is neural network. And all of those methods are supervised learning. So we have response variable and predictor variables. So we have similar setting as regression analysis. And it can be applied for both categorization, classification problem and the regression problem. And you may have more than 2 categories. Oh, sorry, for tree-based methods and yeah, I think the tree-based methods that we have the multiple categories. We can have multiple categories. Support vector machines, for classification, we only have 2 categories. So it's similar to logistic regression. And a neural network, it can be applied for any classification problem, more than 2 categories. And tree-based methods. So this is basically similar to regression analysis, but we separate cases. For example, we have already studied the spline, so which can separate the interval into 2 pieces, and you fit the third degree polynomial on each region of the domain. But the tree-based method generalized it a little more. For example, we have x1 and x2 as predictors. So we have a plane, right? So predictor space is a plane. So we can separate it into several pieces. And on each piece, we fit, for example, linear regression, multiple linear regression. So that is the tree-based methods. And we have several materials which have slightly different models. Just the usual tree-based methods, and also some random forests and some others. So the methodology to split the entire predictor space into several pieces are slightly different. So tree-based methods. And the support vector machine. Support vector machine is also the supervised learning, and the idea is we map original data space into higher dimensional space, then do regression analysis. So think about, for example, regression with interaction and the quadratic terms. Originally, we have x1 and x2 as predictors. So simplest model is y regress y on x1 and x2. But we learned that if we use x1 square or x1 x2 or x2 square, then we have more predictors, so possibly the performance is better. So support vector machine generalized that idea. So we have more more predictors based on original predictors. So if we have x1 and x2, and suppose we have 100 observations, then 100 observations, that means we can have up to 99 predictors, right? So if we have more than 99 predictors, then that is basically redundant, and we have to do some regularization method to, you know, make the algorithm converge. But okay, so if we have 100 observations, basically if we have 99 variables plus intercepts, then we can explain the data completely. So we have more room to expand the number of variables, right? So basically, the support vector machine use some mathematical methods to map the predictor space into higher dimensional space. If 100 observations, 99 dimensional space, then we fit the regression in that, you know, expanded space, then we summarize the result. So that is the idea of support vector machine and support vector regression. Yeah, and a neural network is basically multiple layers of logistic regression. So think about the linear regression. We have, for example, x1 and x2, and response variable is y. Okay, so we can regress y on x1 and x2. And the neural network has intermediate layer. So I would introduce the Z1 and the Z2. Okay. And we fit Z1 on x1 and x2, linear regression. And we fit the Z2 on x1 and x2, linear regression. Okay, so Z1 and the Z2, so intermediate layers. So what should I say? Z1 and the Z2 are unobserved variables. Okay, so but conceptually that we fit the Z1 on x1, x2, and the Z2 also Z2 on x1 and x2, and we regress y on Z1 and the Z2. Okay, so maybe it's better to use some. Yeah, so okay, so in linear regression, it's relatively simpler. If we have two predictors x1 and x2, then we fit the y on x1 and x2. So the model is the y is equal to maybe beta naught, but the beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. Okay, so I'm explaining neural network. And the neural network, basically, that we have two layers or more than two layers. So x1, x2, and we have some unobserved, the variables z1, z2, and we have y. And suppose we are doing linear regression to regress z1 on x1 and x2, and z2 on x1 and x2, and y on z1 and z2. Okay. Then actually this model is nonsense, because if z1 and z2 are linear combination of x1 and x2, and y is the linear combination of z1 and z2, anyway, y is a linear combination of x1 and x2. So this model makes no sense. But if this is not linear regression, logistic regression with the estimated probability z1 and z2, actually this transformation is not linear. So if we think about the two layers of regression, we can express more complicated relationship between y and x1 and x2, right? So, okay, so think about the case that the z1 is equal to, okay, so x1, so maybe we need many numbers, but okay, suppose alpha naught plus alpha 1, maybe alpha 0, 1 plus alpha 1, 1, x1 plus alpha 1, 2, so 2, 1, so alpha 2, 1, x1 and the Z2 is equal, yeah, and we have this one, but we have some transformation here. So we think about some function G, and we transform this linear combination. And Z2 also we consider the sum transform, basically a kind of the logistic function. So logistic function of, so G is logistic function. Logistic function of the this linear combination, and the Z2 that we have the same thing. So alpha 02 plus alpha 12x1 plus the alpha 22 x2. Okay. Then again, we think about the y is equal to g of beta 0 plus beta 1 z1 plus beta 2 z2. Then that we consider sorry, the last one that sometimes we don't have g. Okay, so if we consider this, the y is very complicated function of x1 and x2, right? So we can express the more complicated relationship between z and x1 and x2. So, you know, in mathematics, most idea is to make things simple. For example, some function is linear and another function is linear, then composite function is also linear. So we make it simple. But the neural network, the idea of neural network is to make things more complicated on purpose. So if G is complicated function and we think about the composite function of G and another function, then that becomes more complicated function so that we can represent we can, you know, deal with more complicated relationship between X and Z. So that is the idea of neural network. So we think about the multiple layers of logistic regression, basically. Actually, the last layer, we may not have logistic regression because if Y is continuous scale, we need the entire real numbers as the, you know, the response space. So we don't have the logistic link for the last layer, but basically, if we combine multiple logistic regressions, yeah, multiple layers of logistic regressions, then we consider more complicated relationship between the Y and X. So that is the base idea of neural network. So chapter 8 to chapter 10, they deal with these methods. So, you know, at this point, your plan may be, for example, to compare logistic regression with LDA, but later we will study more methods. So you can compare those with other methods, such as, you know, tree-based methods or neural network or support vector machine. So the plan is your tentative plan, so you can change the plan later. So just I want to see your plan because you are on the right track for the final project and the plan is feasible and the data is good enough, and so on. Okay. Do you have any questions about final projects? Okay, so some of you have done the STAT 5030 final project, and I would say that the difference, the biggest difference is that we have the model comparison in 5820. So we have some models more than linear or logistic regression. So we have multiple methods. So you're supposed to compare the more than one method by, you know, reasonable criterion, such as cross-validation, maybe sometimes validation approach. So that is maybe the possible biggest difference between 5030 project and the 5820 projects. Yeah, on the other hand, sometimes you may have less interpretation of models. I mean, model diagnostics, maybe. Certainly it's harder to do model diagnostics for more complicated models. So that part, maybe you may have less contents compared to diagnosis on linear regression. Okay, so if you don't have any question, we continue the chapter 7, and also that we want to do our implementation of chapter 7. So chapter 7 have many sections, and many sections. So we have many examples on how to use R. And the slides are available on the website, so you can check Canvas. Okay, so last time we did splines. So polynomial regression, step functions, and the basis functions, and the smoothing, the regression splines, smoothing splines. Yeah, and today I want to do local regression and generalized additive models. Yeah, so chapter 7.1 to 7.5 are similar models each other, but the 7.6 and 7.7 are a little different. So 7.6 is local regression. The local regression is non-parametric method, non-parametric version of regression. So what is non-parametric? Non-parametric means the model is not determined by the fixed finite number of parameters. So parametric, that means model is based on a fixed and finite number of parameters. So based on fixed finite number of parameters. And non-parametric, it's not. So what does it mean when we say fixed and finite number of parameters? That means the number of parameters does not depend on sample size n. So in linear regression, if we have 10 observations and suppose maybe 2 predictors and the intercept, n is equal to 10 and the number of parameters is equal to 3. But number of observation is increased to 100. Still, we have 3 parameters. So we have fixed number of parameters. But the non-parametric methods, in non-parametric methods, the p increases when n increases. For example, suppose n is equal to 10, maybe the p is equal to 5, but n is equal to 100, then p becomes 50, and so on. So, of course, for a finite data set, everything can be explained by finite number of parameters, but if it increases as n increases, then we say it's non-parametric. Yeah, and so suppose we want to predict y for a given x. A simple function that typically the straight line is fitted only with a certain proportion of observations which are close to the x naught. So this is the local regression. So suppose that we have 1,000 observations, but the data ranges widely in the domain. So only relevant observations are just observations close to that observation. Right. So for example, I would say that you are maybe we are diagnosing if a patient is overweight or not. And that criterion is based on age, right? So usually the babies are chunky. So when we see 70 years old, when we see if the 70 years old lady is overweight or not, we don't use the data for babies, right? So probably it's good to use just the data set whose profile is similar to the 70 years old lady. So maybe age 70, maybe 65 to 75. Then we take the average weight of maybe average BMI of those people to see if that patient is overweight or not. So we use only local information to see something. So that is the idea of the local regression. Okay, so and also that we give a higher weight on observations, very similar to our intended observations, our target observation. For example, we are seeing if a 70 years old lady is overweight. Suppose we have 10 observations, the one at age 65, one at age 66, and one at 70, one at 71, and one at 74. Then we give higher weights on the similar people. So maybe if their age is 69 or 70 or 71, that we give higher weights in the linear regression. So I mean, the linear regression is done by minimizing sum of squares, but we put coefficient. We put the coefficient to when we calculate the squared residual. So that is the idea of local regression. And one parameter we have to choose, one hyperparameter we have to choose is the proportion of observations which are closer to x naught. So suppose we have 1,000 observations, and what proportion that we should take to make a prediction on the target observation? Maybe 10% or maybe 1% or 100%. It may depend on the sample size, but also it may depend on the complexity of the relationship between x and y. If the relationship is simple, just we can use all observations. But the relationship is more complicated. Probably we have to use the observations very close to that observation, right? So suppose that so in simple case, all observations have the same tendency. So even if we have 1,000 observations, I cannot write 1,000 observations right now, but if we have many observations, but this relationship is so simple, so just we can use all observations to identify the relationship. But if the pattern is very complicated, like this, maybe even more complicated, such as maybe like this, the probably fitting a linear regression using all observations does not make much sense. For example, maybe new observation has x value of here. Then probably we have some peak here. So our estimate is like around here. But if we use all observations, probably the fitted line is like this. So it's far away from the local estimate. So in this case, we have to use the small s, small proportions to be used. And maybe in this case, we can use all observations to fit the model. So we have to decide S. Yeah, and generally the large S makes the F hat smoother, right? So if we use more observations, we have the smoother fitted line. We have studied nearest neighborhood method, and if we make S larger, basically the rule is simpler and the result is smoother. Yeah, so that means the variance of F hat X smaller. So we use many observations, so the estimate is more reliable, but the bias is larger. So you can see that if we use this method, you know, the straight line for this data set, then bias is large. Probably the true expected value of y when x is equal to x0 is around here, but our estimate is here, so bias is large. So we have trade-off between the variance and bias. Larger S, variance is smaller, but bias is larger. S is small, S is more unstable, variance is larger, but bias is smaller. Yeah, so that's the overall picture of local regression. And so this method has also another difficulty. So basically, we are given X, we can estimate Y hat, but the algorithm really is different for all X. For each X value, that we have to choose the closest, maybe 100s% of observations, then we fit the model. So for each X, we have to estimate the model. So actually, we cannot estimate the fitted value at all possible X, because we have infinitely many X on the X-axis, but we can estimate Y for some specific X, maybe with increment of 1, or is increment of 0.1, or for all observed X values. So we have to compromise it some way, but at least for finite number of X's, that we can estimate Y hat. Yeah, so this is an image on how local regression is fit. So suppose that we want to estimate Y value. So this is X value, and this is Y value. And given X naught, we want to estimate Y hat. And how to estimate it? At first, we select S. Probably here, S is about maybe 25%. So we pick up the maybe 1/4 of entire data set. So maybe it looks we have 100 observations. So we choose maybe 25 observations. Maybe 20, maybe I don't know, maybe S is 0.2. 20 observations. Then, okay, so these red circles are observations to be used to calculate Y hat. And once you picked up the 20 closest observations to X naught, we give weight. Then we fit this straight line. You know, the simplest case is maybe we fit just the constant for these 20 observations. So just the local average, but the local average may not be optimal. So you can see that if X0 is this value, actually only 1, 2, 3, 4, 5, 1, 2, 3, 4, maybe 5 observations are less than X naught, but the years of 15 are more than X x naught. So that means that we may have bias. We have some tendency like this. So if we have only 5 observations to the left and 15 observations to the right, we may have some bias. So it's better to fit a straight line rather than just the constant value. So we fit the straight line on these 20 observations. Then we think about the value at x is equal to x0. So that is our estimate for y. So I would say y naught hat. Yeah, and also within these 20 observations, these observations are relatively less important because it's a little far away from x naught. So we give lower weight. So that is represented by this, the green, the bell-shaped curve. So we give higher weight on observations close to this x naught, but the lower weight on these observations. So lower weight means that when we minimize the sum of squares, so usually we minimize epsilon I square, maybe I is equal to 1 to 20, but we put weight, so summation of wi epsilon I square, I is equal to 1 to 20. Okay, and the wi is larger when observations are closer to x naught. And this is actually the same data and the same thing. And the actually the number of observations may be different. In this case, probably S is slightly larger. It looks S is about 0.4 or 0.5. And also X0 value is here. So it's more like the center of the data. And we use these observations, these red observations to fit the model. And this yellow line is the estimated curve. And the blue line is the true curve. I mean, behind the simulation. So blue is the true one. This is the true curve. And this is the estimated curve, by local regression. Yeah. Probably yeah, probably this figure shows that the S is pretty large number, such as 0.5 or something, maybe even the close to 1. But the we only colored these observations red when weight is larger than some value. So that's why we have only 20 observations here and probably have about 50 observations here. So, not necessarily that we have to have a small s. Even s is large, that we have the weight, higher weight only for the observations close to x naught. But still local regression works well. So probably, yeah, probably this is, s is larger probably. These have the same s, but the s is large. Maybe s is, I don't know, 0.5 or 1.0. But the weight is higher only when the observations are close to x naught. So on the right pane, the many observations are closer to x naught. So it looks the more observations are given weight. Yeah, so this is the more detailed algorithm written in sentences. So to estimate f hat of x naught by local regression, at first find 100s% of observations which are close to x naught. Here s is maybe 0.2, maybe 0.5. And let x1 to xk be such observations. And assign weight k, xi, x naught, and k of xi x naught is larger when xi is closer to x naught. And k of xi x naught is 0 if xi's are not among the k closest point to x naught. So typically k's are functions such as a bell curve exponential of maybe xi minus x naught square over 2, maybe negative, like this. So if xi is closer to x naught, then value is larger. If xi is distant from x naught, then the value of k is smaller. And this is basically depends on the distance between xi and x naught. And then we minimize this weighted residuals. So k of xi x naught times this one. This one is basically epsilon I. So yes. Then after we estimated beta naught and beta 1, we define f hat of x naught as this. Maybe to be exact, this depends on x naught. So maybe I have to say beta naught hat of x naught and beta 1 hat of x naught. But we use these coefficients to estimate the f hat of x naught. Yeah, so this is the how local regression works. Do you have any questions? Yeah, so the most basic idea behind it is, calculating local average. But this is more sophisticated in the sense that we are not calculating just local average, but we fit regression model on, local information. And by fitting straight line, the bias is smaller than just calculating the local average, because local average, you can see that some observations, only a few observations are on the left-hand side of this observation, and the larger number of observations are on the right-hand side. So in such a case, if we just calculate the local average, that can overestimate the y0 hat in this case. So fitting a straight line is better. But as you can see, probably we don't have to fit a very complicated curve. For example, the quadratic curve is not necessary. Probably just straight line is more than enough. And if we want to make this estimated curve more detailed, just make s smaller, or just we make the, the weight function, the k of xi and x naught. So this is narrower than, this is large number only when xi is very close to x naught, then the estimated, the curve by local regression is the more complicated and the less bias, has less bias. So probably the straight line is enough for local regression. If we only use intercept, it's okay, but probably it's not as good as straight line. Probably we don't need more than that. Theoretically, we can fit more complicated local curve, but that isn't necessary. Yeah, so do you have any questions? Yeah.
I had a question.
Yeah, sure.
Just because I wasn't sure. On slide 18, how come the highlighted part for the second graph is?
Yeah, sorry, I'm not exactly sure, but my impression is that the S is large. S is very large number, such as 0.8. And the circles are colored red if the weight is large enough. That is probably the reason.
Okay, thank you.
So yeah.
Just wondering.
Yeah, probably. I'm also wondering, but probably, yeah, that's the case. Yeah. Yeah, it's not clear. Yeah, any other questions? So local regression is probably a very useful method when you fit complicated curve. Yeah, when I was doing the sample design in a bank, we discussed that we cannot avoid bias when we use the local average. But at that time, I didn't know the local regression. But if we can use local regression, then we can reduce the bias. Yeah, so at that time, my issue in a business survey is that we're just calculating the average sales or average profit or average investment of a company. But when we send the questionnaire, larger companies respond with a higher rate. So if we send the questionnaires to companies with 1,000 employees, we can get maybe 99% response rate. But if we send those questionnaires to a company with only 1 or 2 employees, then the response rate is very low, such as 30%. So in that case, we have to do something, right? So if we just take average sales, then companies with larger sales respond with a higher rate. So the sales is more overestimated, right? So, but probably if we use local regression, then we can estimate the sales of companies better. So here, I mean that X is maybe number of employees, and Y is sales. So number of employees larger, the sales is larger. But if we use just the local average, then even among the neighborhood of specific X naught, still the more companies with higher number of employees answers with a higher rate. So estimated sales is overestimated. So probably local regression is better. Yeah, I think the survey results that we need more statistical method in the United States. Right? So for example, the communist countries that are planned economy and the government is stronger, so they can get more accurate data. So they don't need really, advanced statistical methods. United States or other, capitalism countries, basically people have more freedom and the companies don't respond to the questionnaires, especially if the information is more confidential, such as the price information. So we have to have more advanced the estimation technique to get some estimates, even census. Yeah. Yeah, if you're interested in statistics, it's good to go to the Census Bureau. There are many statisticians. I heard the 250 statisticians in census, maybe 300. And many international students who are strong in math get a job in US. So the many jobs are competitive, but those Census Bureau of Labor Statistics, those institutions are governmental, and international people cannot get a job, so less competition also. Okay, so 7.7, the generalized additive models. So this is totally different from 7.1 to 7.6. Only the common thing is that to deal with something beyond linearity. And we consider multiple variables in this section, so x1 to xp. And we consider the relationship between response and the multiple predictors x1 to xp. So generally, y is a function of x1 to xp. So this can be very complicated function, such as maybe x1 plus the square root of x2, x3 plus x4 cube plus maybe the sine of x5 plus square root of x1 plus x3, x4, or something like that. But it's too demanding to identify this kind of function. So the generalized additive models assume that we don't have any interaction between predictors. So we don't allow x2 times x3. Also, we don't allow this kind of function. So inside the square root, we have x2 times x3 and x4 square. So this is a linear, so that means that we cannot separate the impact of x2, x3, and x4 on y. So we don't allow that possibility, and we assume that yi is the beta naught plus summation of fj of xij. Sorry, maybe this is a little bit unclear, but this I means ith observation. And this j means the jth variable. So we have p predictors. So j is equal to 1 to p. And we have we have n observations. So I is equal to 1 to n. So yi is equal to summation of fj of xij plus epsilon. Yeah, so typically, for example, we have beta naught plus maybe the beta 1, 1 plus beta 1, sorry, beta 1, 0, maybe beta 1, 0, sorry, 1, 1, beta 1, 1, sorry, I'm a little confused. Beta 1, 1 times x I1 plus maybe beta 1, 2 times xi2 square plus, for example, beta 2, 1 times xi2 plus maybe beta 2, 2 times x maybe I2 maybe square root and plus something like that. So we have more than just linear term, but the effect of x1 and sorry x1 sorry so effect of x1 and the effect of x2, effect of x3 up to effect of xp are separated. So that is the assumption of the generalized additive models. And of course, we need additional assumptions on what is f. F may be polynomial, f may be basis functions, f may be step functions, f may be spline. We need some assumptions on f for each variable xi, but xj. But basically, we combine the several of these to fit y. So this is generalized additive model. Yeah, so this is one image of GAM. So we want to fit wage on year worked and age and educational level. So this is the relationship between wage and year. So we fit wage on the year, and we have inflation over time. So recent years we have higher wage, but we have not straight line, maybe because of the business cycle. The maybe 2004 to 2006, the economic condition is very good, so we have higher increase in wage. After that, we have recession, so we have the lower growth in wage. And this is age and the wage, basically. So we fit wage on age by probably spline, and the age between maybe 35 to maybe 60, the wage is higher than lower age or higher age. Nonlinear relationship. And this is education versus wage. So educational level is higher, then wage is higher. So we don't have any legend here, but probably the no label, but this is maybe high school dropouts, high school graduates, and maybe some college courses, maybe college degree and graduate degree or something like that. Yeah. So these are profiles. So to be exact, so they fit probably the model. Okay, so suppose this is X1, X2, and X3. Then these are the result of GAMs. So we fit wage on, so these variables. So constant plus, I don't know this one, maybe, spline. So spline of X1 with some degree and plus spline of X2. And the last one is probably factor variable. So for each level of X3. So X3, maybe high school graduate, less than high school. Oh, I see that this is level. So less than high school. And sorry. So we need the indicator function for each category. So maybe we have the indicator function for less than high school and the indicator function for high school and the indicator function for less than college and so on. So we have maybe one coefficient for each. So beta 3.1 and beta 3.2 and so on. And the plus epsilon. So this is the model, and the estimated spline curve is here. Yeah. And sorry. So this is the so this is estimated by least square method, but it's not clear what kind of variables in it. Maybe polynomial regression, maybe they are fit. Sorry, so maybe not spline, maybe polynomial. I don't know what's the degree of polynomial. Maybe this one, 3-degree polynomial, maybe, and this is more complicated, maybe 4-degree polynomial or something like that. And this one is by spline. So this is the spline, and this is spline, and this is probably the same. So indicator functions for each level. And always that we can fit we can apply this kind of methods for logistic regression. So polynomial regression also, if y is continuous scale, then we can fit polynomial regression as this. But also we can fit the logistic regression. So logistic regression, the probability of y is equal to 1 is equal to beta naught plus beta 1x plus beta 2x squared. So always that we can think about the logistic version. So the GAM can work for logistic regressions also. So if y is binary response, then we set the p of x. So sorry, we explain the probability of y is equal to 0 as a function of x. So this one is equal to this. And if we have predictors x1 to xp and we apply the generalized additive model methods, then just we assume that the log of this, yeah. So basically So this is the inverse logit function of the P of X. So this is equal to this function. So we can apply the GAM idea to logistic regression. Yeah, so this is how GAM works. Any questions on GAM? Yeah, so often we need some simplification. So of course, interaction terms may be important, but we cannot think about all possibilities. So we simplify the situation. Yeah, still, if you are thinking about specific interactions, then you can increase the number of variables. So if you really want to include interaction between x1 and x2, then just you can add x1, x2 as another predictor. Then you can include it in the GAM. But that means that we don't consider interaction between x1, x2, and x3. We don't have to, we cannot account for this interaction. But if you want to include specific interactions, still you can introduce it as the original predictors. Okay, so now the chapter 7 lab session. So example for each of the methods. So polynomial regression. So this is the Nile River water level data since 1871. I mean, from 1871 to 1970. So the Nile River water level is going down, but we have some complicated pattern. Probably this higher period and lower and slightly higher here, like this. So we want to estimate, we want to fit a curve on this. And first, the polynomial regression. So we fit the polynomial regression. You have already done several times. And for this one, okay, so this is linear regression. So intercept and first term. And the polynomial, that we can use the polynomial regression term. So here. So intercept and the polynomial and 1 and the polynomial 2. And this is not just the time and the time square. So this isn't really the time and time square. Because this is orthogonalized. So this is actually the first component. So time 1, polynomial time 1. And this is 2. So first term is linear and the second term is quadratic, but not exactly just time and the time square. And actually we made it the 2 components orthogonal. So if we consider correlation between x1 and x2, so I would say this is x1 and this is x2, then correlation between x1 and x2 is 0. Yeah. And if you want to really fit the model of y is equal to beta naught plus beta 1 time plus beta 2 time square, then you can code in this way. So polynomial time 2 and rho is equal to t. Or you can also write as this way. So time plus the I of time square. Then you can get these coefficients. So these coefficients are, yeah, so this beta 1 and beta 2. And you can see that still these are statistically significant, but the p-value is less significant here. So you can see the previously, the first one is much highly significant. So p-value of 0. I mean, 2 times 10 to the power negative 7, so very small. But here, the p-value is not that small. So in this case, it's still significant. So we don't see too much trouble here, but it's larger, less significant. And the reason is here. Okay, so probably this label is not is a little bit misleading. So the X value is the time. So that means the 1871 to 1970, right? So this is time. Okay. So you can see the scale this is 1 million. So the time is about 10 to the third power. So almost 0 in this graph. And here, this is time square. But the time square is what? The 1871 square, it starts with 1871 square and it ends with 1970 square. But anyway, so these numbers are similar. About 2000 square, right? So it's almost flat line. So that means that this one, time and time square, has higher correlation. So correlation, I didn't report the correlation, but they're probably more than 0.9. So that means we have multi-collinearity. So we have less significant p-values. And also we may have some convergent issues or computational issues. So time square is more than 1 million, about 4 million. So we have some problem about the overflow of calculation. Maybe 1 million is maybe okay, but if time to the 4th power or 5th power, we may have trouble. So that's why the first way, orthogonal components is usually better. But still, sometimes we really want to fit this model itself. So you have an option to fit this model. Okay, so this is polynomial regression. And also that we compare the several fitted curve polynomial regression with degrees 3, 4, 5, 6, 7. How good these are. And we start with the straight line to 7th degree polynomial, and the result is here. And obviously, the black one is the first one. So this is the degree 1 polynomial. And the degree 2 is red, in R. So I differentiate color, and the color 2 is red. So red one is degree 2. And the green is the third one. So this is degree 4, degree 3, sorry, degree 3. And the degree 4 is, I think, the blue. The blue one is around here. So this is degree 4. Oh, 1 to 3 is here. And 4 is blue. And 5, I'm not sure, maybe purple. And 6 is the light blue, maybe. So you can see that these are fitted lines. And which is the best one? Actually, the dotted line is what? Yeah, actually, the last one, sorry, the 7th one is the dotted line. So the dotted line is degree 7. And what is the best one? We cannot see it because we don't have the answer. But it seems like, I don't know, maybe 2 or 3 is sufficient. I would say maybe 2 or 3 is sufficient. And the 4, 5, 6, 7 looks unnecessarily complicated, but yeah. And we can calculate AIC value. Actually, my intuition is not really correct. And probably degree 4 is the best because AIC is smallest. Degree 7 is also small, So it's not entirely clear what is the best one, but usually AIC is similar, then we choose a smaller model. So maybe the 4 is good. I don't know which value, maybe 7 value looks slightly smaller, maybe almost the same. Yeah. AIC residual, yeah. And this is another table that to see if additional component is significant. So you can see the 3 stars here. So that means the 2 components is significantly better than 1 component. And actually the 4 component is significantly better than the 3 components. And actually 7 is significantly better than 6. So maybe the 7 is good, but the 4 and 6, 7, not much difference. And another one is logistic regression. So we see what's the probability that the water level exceeds 1000. So this is, y is equal to 1, and here y is equal to 0. And we fit logistic regression. So probability is higher here and slightly higher here, maybe flat, I'm not sure. So we define y as Nile water level is more than 1000, and we fit GLM. So remember that we have to fit the family is equal to binomial. If we drop this, the GLM is the same as LM. And we fit time, the degree 2 polynomial of time and the degree 3 polynomial of time. Then what's that? So at first, the linear term is statistically significant. And the second term is marginally significant or marginally insignificant. The p-value is between 0.05 and 0.1. So the third term is certainly almost useless. And if we see AIC, the degree 2 is the best. So that means this figure that you can see we have some nonlinear pattern in the probability. So probably it's higher here, but not much lower here. So we have this kind of curve. Yeah, so this is 7.1, and yeah, I think it's already 6:44. So we cover 7.2 to 7.7 next time. Yeah, so see you on Thursday.
Have a good night.
You too.